In this video, we're going to be using a position time graph to create a velocity time and an acceleration time graph. But our position time graph that we're starting from is a bit tricky because it's all curved. So this is the graph of the height, so our position here is height, of a ball that's being thrown straight up into the air. So it starts moving up really quickly, slows down, stops at the top, and then speeds up going down. It makes a parabola shape. You've seen this in math class, I'm sure. What we want to know is what are these velocities at all these moments in time so that I can create a velocity time graph. But because it's curved, it's hard to actually see the slope. So what we do as a little trick to figure out the slope at a point is we draw what's called a tangent line. So tangent line means you want to go into your curve and you want to go as close as you can to the quadratic that we've got here. And we're going to draw a line that is parallel to our curve at a certain point, but not I'm not going through it, just nice and parallel. It's a bit tricky sometimes. Try and get one that looks okay here. Maybe something like that. Alright, that is an okay tangent line. It's decently parallel at that point of 2 seconds. So that would be my tangent at 2 seconds. I'm going to do these tangent lines at every single point. We'll just start with 2. Just because it's easy and exposed. Then I have to figure out the slope. So what I'm trying to find is the velocity at 2 seconds. The velocity is the slope of this position time graph, right? So the slope here, I'm going to pick any 2 points on the line. I'll pick these 2 because they seem to kind of intersect at places on my graph. You can actually pick any points you want. You could pick the point itself, that would be fine. I just like to pick points that kind of go through part of the grid, right? So this is a nice point because it kind of rounds off at like 35 and in this direction around 1.5, right? So that just seems like a nice point for me to pick. This one seems to be around 45 right here. This is like from 1.5 over to, this looks like right on 2.5. Okay, so my slope is the y2 minus the y1 over the t2 minus the t1. So my final height, it reaches 45 minus my initial height, this one, the 35 here, over the t2, so it's 2.5 is the final point that I chose, and 1.5 is the initial one. You should actually get the same slope no matter which points you choose. So you could do this again with this point and maybe the point on the line itself, and you should still get the same slope, or at least close to it. The unfortunate thing about this method is that it's definitely approximate, right? You can feel that even how I draw my tangent line, like there's a few answers in here that are pretty similar and it's kind of hard to see which one is exactly right. It's inherently inaccurate doing this method. Fortunately, next year, hopefully you will take calculus, which is my favorite math course, and then you'll learn a way to do this, to find tangent slopes absolutely precisely using some really beautiful math, which is great. But we don't have that math right now, so we have to use tangent slopes. Here we are. Okay, so 45 minus 35, that's 10. 2.5 minus 1.5, that's 1. So my slope is 10 meters per second at 2 seconds. What I want to do is make a velocity time graph. So that means I'm going to need to know the times. That's going to be my horizontal axis, and my vertical axis is going to be not displacement anymore, but velocity, which is the slope, right? So that's what I'm going to make a little chart of here for each of the times that are on this graph. So I'll have 0, 1, 2, 3, 4, 5, and 6. So I've already done 2. So at 2, the velocity is 10 meters per second, so I can fill that in. Now I just have to go and do that for all the other points. So let's start at 0. I want to make my line nice and parallel here. It's tricky, something like that. Get a little closer. There's a nice parallel line. Then I'm going to need to pick 2 points. A really good one to pick would be 0, 0. That's a very easy point to choose because I can here. Otherwise, it looks like it goes through 15 and 0.5, so that looks like a good one. I'll draw my rise and run triangle. The slope here is going to be my y2 minus y1 over t2 minus t1 as always. So that slope will be my final height here is 15. My initial one was 0. My final time for the point that I chose here is 0.5 and my initial time is 0. So 15 divided by 0.5 is 30 meters per second. So I can fill in the velocity at 0 is 30 meters per second. So that means when this ball is initially thrown up, it's leaving someone's hand, it's leaving at 30 meters per second. We'll keep doing this. We'll do it at 1 second here. So try and make this nice. There we go. I think I'll do my rise over run triangle just like this between these 2 points. They're both on my line. Kind of nice points. I've already used them before. So my slope of that is going to be my y2 minus my y1 over my t2 minus my t1. So y2 is this point right here, that's the 35. y1 is down here, this point, that's the 15. t2 is the time that goes with that guy, so 1.5. t1 is the 0.5. That gives me 30 minus 15, which is 20, over 1.5 minus 0.5, which is 1, so 20 meters per second. All right, my slope at 1 second is 20 meters per second. Next, 3 seconds. This one is a nice easy one. So here, when I draw my tangent line, you can see that the slope here is horizontal. That slope is 0. That makes a lot of sense. This is an object being thrown up into the air. At the top of its trajectory, it's been moving up. It has to stop, turn around, and then it can go down again. So it stops briefly at the top. So the slope at the top, the velocity at the top, is 0 meters per second. Let's move on. Let's do this one here. So this is at 4 seconds. Then I'll find 2 points that kind of work. There's one there. Here's one here. Draw my little triangle. So the slope here is going to be y2 minus y1 over t2 minus t1. My y2 looks like it's 35. My y1 is the 45. My t2 is 4.5. My t1 is 3.5. So that gives me negative 10 on top and 1 on the bottom, or a slope of negative 10 meters per second. That shouldn't be surprising at all to us. This is a quadratic, so this side is exactly the mirror image of this side here. So if the slope here was positive 10, the slope here should be negative 10. Right? So this is going to be negative 10, and you can just carry the pattern down. Don't have to do your tangents for all of these. It's clearly going to be just the downward slope that's reflecting this one. So 5 seconds must have a slope of negative 20 meters per second, and 6 must be negative 30 meters per second. All right, now that we've got that chart, we're going to use it to create our velocity time graph. So here's our velocity time graph. All right, I'll keep my chart off to the side. So what I know is that at a time of 0, the velocity was 30 meters per second. So I do a point here at 30. At 1, the velocity was 20. At 2, the velocity was 10. At 3, the velocity was 0. At 4, the velocity was negative 10. At 5, it was negative 20. At 6, it was negative 30. Once you've got those points in there that tell you the instantaneous velocities at all those moments, then you get to just connect the dots. It's a nice smooth curve. There's nothing weird going on here. So it's definitely fair to assume that this will be a nice straight line. And it is. So we'll just connect all those dots. So that is our velocity time graph there. My next job is to make the acceleration time graph. So that means I need to find the acceleration of the ball. So acceleration is actually just the slope of a velocity time graph. So it's going to be the v2 minus v1 over t2 minus t1. And I get to pick any 2 points that I want on this graph. Maybe I'll just do them in color. Maybe I'll pick this one here. Looks like a nice one. And maybe this one here. It really doesn't matter what you choose. So my v2 then is 0 minus my v1. This point here, it has a velocity of 20. So 20 here. Oh, this marker is dying on me. Yeah. My t2 is the time at that point, which is 3, minus my t1, which is 1 right there at that point. And then I can put that together, so I get on the top negative 20, and on the bottom 3 minus 1 is 2, which gives me a slope of negative 10, and the units are meters per second squared. So my acceleration is negative 10 meters per second squared. That's the slope over this section, but it's the slope for the entire thing because it's just a straight line. It's not curved at all. So unlike our position time graph, we don't have to do any weird tangents here. We can just calculate the slope of the whole line. All right, so I've got an acceleration of negative 10. I can graph that. So acceleration of negative 10 looks like this. Go to the negative 10 part and just make a horizontal line. All right, there's my acceleration time graph. It turns out that that's actually a very special acceleration. So that is the acceleration of every single falling object if there's no air resistance. So if you throw a ball in the air, it'll accelerate downwards at around negative 10 meters per second squared. If you throw a guitar in the air, I don't know why you do that. I was just looking at a guitar beside me here and thought of a guitar. If you throw that in the air, it's going to accelerate down at negative 10 meters per second squared. If you jump in the air yourself, you're going to accelerate downwards at negative 10 meters per second squared, approximately. That has a symbol, so that acceleration is the acceleration due to gravity. That's what the acceleration that our gravity creates on you. It has a symbol lowercase g. We'll be using it a ton in this course. It's also called the gravitational field. You're going to dive into field and concepts of gravitational field a lot more deeply in grade 12. So everybody's going to accelerate downwards at g on the surface of the Earth. Every planet has its own acceleration due to gravity, by the way. So you can calculate little g on other planets too. It doesn't matter what the mass of your object is. It will still accelerate down at around this 10 meters per second squared down, or negative 10 meters per second squared. G has a value more precisely in Oakville, so it's actually not exactly 10. It's actually more precisely 9.81 meters per second squared in Oakville, and G actually has slightly different values at different points in the Earth. As you go up mountains, you get a little bit further away from the center of the Earth, and your acceleration due to gravity actually decreases a little tiny bit. As you go towards the North Pole, you're a little bit closer to the center of the Earth because the Earth is kind of egg-shaped, and so your acceleration due to gravity increases a little bit. But around Oakville, G is approximately 9.81.